Ever needed to process server logs, track operation progress, and handle LLM sampling requests, all through a single, clean client interface? We'll set up a FastMCP client with 3 dedicated async handlers: a log handler that prints incoming LogMessage objects, a progress handler that displays operation status with support for both determinate and indeterminate progress, and a sampling handler that receives a list of SamplingMessage objects, including text, image, or audio content, optional sampling params, and request context, then returns generated text. You'll see how the client maintains a persistent connection while keeping each handler focused on its specific task, with proper type safety throughout. From FastMCP import client. From FastMCP client logging, import LogMessage. Async def log handler message, LogMessage. Print f server log, message data. Async def progress handler, progress. Float total, float none message, SDR none. Print f progress, progress/total, message. Async def sampling handler, messages, params, context. Hash integrate with your LLM service here. Return, generated response. Client equals client. My MCP server, pi. Log handler equals log handler. Progress handler equals progress handler. Sampling handler equals sampling handler. Timeout equals 30, 0. This demonstrates the event handler pattern for server-client communication in FastMCP 2, where specialized async functions process different server-initiated events through a maintained connection. The code establishes 3 distinct handlers: one for server logs, one for operation progress updates, and one for LLM sampling requests. Unlike traditional request-response models, this pattern enables the server to push events to the client as they occur, with each handler processing a specific event type while the client maintains the connection. The pattern works through clearly defined handler interfaces that match FastMCP's protocol specifications. The log handler receives structured LogMessage objects containing time-stamped server output. The progress handler uses a standardized signature where progress and total are floats, and message is optional text, with none as total indicating indeterminate operations. Most significantly, the sampling handler implements the server-initiated LLM request pattern, receiving 3 parameters: a list of SamplingMessage objects, each containing role plus content like text content with its text attribute, sampling params with optional model preferences, and request context for session metadata. All handlers operate asynchronously within the client's persistent connection, ensuring non-blocking processing of server events. This approach matters because it provides structured handling of server events without transport-specific coupling. The pattern excels in AI integration, scenarios where you need to respond to model sampling requests with full conversation context, monitor long-running operations through standardized progress updates, and process server logs with metadata. The persistent connection design makes it particularly efficient for high-frequency interactions, while the clear handler interfaces maintain separation of concerns between event types. The trade-off is the initial handler setup, but the result is a robust system where each interaction type has defined boundaries and type safety through FastMCP's client modules. Let's break it down. From FastMCP import client. From FastMCP client logging, import LogMessage. Imports the client class for maintaining persistent FastMCP server connections, and the LogMessage type that standardizes server log events with timestamp, severity, and payload fields. This provides typed access to structured logs rather than raw strings, while the persistent connection enables efficient server-client communication across multiple operations. The LogMessage class ensures consistent log handling with metadata preservation throughout the application lifecycle. Async def log handler message, LogMessage. Print f server log, message data. This async callback handles server logs by receiving LogMessage, objects containing structured log data. The async design prevents blocking during high-volume logging while maintaining efficient server communication through the persistent client connection. It provides real-time visibility into server-side operations for debugging and monitoring.
Async def progress handler progress, float total, float none message, SDR none. Print f progress, progress/total, message.
This progress handler implements FastMCP's async callback pattern for operation tracking. It receives 3 parameters: current progress, units, optional total units, none for indeterminate operations like streaming, and an optional message string for status updates. The async signature ensures non-blocking execution during high-volume events while the client maintains the persistent connection. The pattern enables real-time progress reporting without blocking the main execution flow, with explicit none handling for cases where total work isn't known upfront. All handlers register through the client constructor using this same async callback pattern.
Async def sampling handler, messages, params, context. Hash integrate with your LLM service here. Return generated response.
This sampling handler implements FastMCP's required callback for LLM sampling requests, receiving 3 parameters: a list of SamplingMessage objects, each containing role and typed content fields like text content text, optional sampling params with model preferences that clients may ignore, and a request context for metadata. The client maintains a persistent connection for efficient server-client communication, with this async design enabling non-blocking handling of sampling events.
Client equals client. My MCP server, Pi.
This instantiates the FastMCP client with 3 async event handlers. The log handler processes structured server logs via LogMessage objects, while progress handler tracks operation progress where total equals none indicates indeterminate operations, introduced in v2.3.5. The sampling handler implements server-initiated LLM sampling requests, receiving messages, list of SamplingMessage objects, each containing role and content supporting text, image, or audio. Params, sampling params with optional model preferences. Context, request context for metadata. It must return the generated text response. The client maintains a persistent connection for efficient server-client communication, with all handlers supporting async operation. FastMCP client handlers. The code demonstrates 3 fundamental asynchronous callbacks: log handler for server-emitted structured logs, progress handler for long-running operation updates, and sampling handler for server-initiated LLM completion requests, all operating over a maintained client-server connection. The sampling handler signature matches the official specification with 3 parameters: a list of SamplingMessage objects, each containing role and content attributes supporting text content with text, image content, or audio content, sampling params that may include optional model preferences clients can ignore, and request context for state management, while strictly returning a string response. Progress notifications introduced in v2.3.5 distinguish between determinate, with total, and indeterminate total equals none operations, with the async design preventing UI freezes during high-volume events, and only progress handlers support per-call overrides via client call tool.
The handler that answers every request speaks only in strings.